All right, welcome back for another deep dive. Today we're tackling some pretty fundamental physics. Work, power, and energy.
Oh, yeah, those are big ones.
They are.
Hmm.
And I think we're going to have some fun uncovering some surprising connections, practical applications you might not expect. Like, we're going way beyond textbook definitions here.
It's true. These principles underpin so much of our physical world, so we'll shed some light on why understanding them matters, from everyday actions to those big, complex systems.
Exactly. So let's start with work, right?
Okay.
We use that word all the time, but in physics, it has a very specific meaning.
For sure.
So imagine lifting a heavy box. You're applying force. You're moving it at distance. Boom, that's work.
Right, and the fascinating thing about work is it only happens when the force you apply causes movement in the direction of that force. So you could be pushing against a wall with all your might, but no matter how much you're straining, no work is being done because the wall isn't moving.
So it's not just about effort.
No.
It's about effort leading to a change in position.
That's it.
Ah, that makes me think about, like, struggling to open a stuck jar, right?
Right.
I might be applying a lot of force, but if that lid doesn't budge, I'm technically doing zero work.
Exactly. That's a great example. And another key point to remember is the force can be constant, like gravity pulling on an apple, or it can vary. Think of a stretched spring. The force changes as it extends or compresses.
Oh, okay. So then how do we measure work when the force is changing like that?
Well, picture a graph, right? Force on one axis, distance the object moves on the other. The work done is actually represented by the area under the curve of that graph.
So it's not just a number. We can actually see work as a shape.
That's right.
That's pretty cool.
It's a neat way to visualize it.
Yeah, it is.
Oh,
Now, this might sound a bit strange, but can work ever be negative?
absolutely. Think about gently lowering that heavy box we were talking about. You're applying a force, but gravity is actually doing the work, pulling the box down. You're opposing the motion. So the work you're doing is considered negative.
So I'm doing negative work because I'm essentially resisting gravity.
Precisely. And here's another interesting thought. If you carry that box horizontally, the work you do is zero. You're using force to support its weight, but the movement is perpendicular to the force, not in the same direction.
Wow. Okay, that's counterintuitive.
It is.
So much of what we do involves force and movement, but we rarely think about the physics of work involved.
Right, right.
Okay, so now how does energy fit into all of this?
Well, energy is often defined as the ability to do work. It comes in many forms: mechanical, chemical, electrical. A moving object has energy because of its potential to do work.
So that's where kinetic energy comes in, the energy of motion.
Exactly. The faster an object moves, the more kinetic energy it has.
Okay.
And we can even calculate it. Kinetic energy equals 1/2 times the mass times the velocity squared.
Okay, so both the mass and velocity are contributing to kinetic energy.
That's right.
So a speeding bullet and a massive, slow-moving truck could have different amounts of kinetic energy.
That's a great way to put it. It's not just about how big something is or how fast it's going. Both factors matter when it comes to kinetic energy.
So this is starting to connect in my mind, right? We have work, which is force creating movement, and we have kinetic energy, which is the energy of that motion. Is there like a link between those two?
There is, and it's a fundamental one. The work-energy theorem states that the work done on an object is equal to the change in its kinetic energy.
Okay, so if I push that box and it speeds up, the work I've done is equal to the change in its kinetic energy.
You got it.
Wow.
And it goes beyond simple scenarios. Think about a car accelerating.
Okay.
This theorem explains why it takes more force to go from 0 to 60 miles per hour than from 40 to 60.
Because there's a bigger change in kinetic energy.
Exactly.
That's amazing. It really ties it together.
It does.
What about power? Does that relate to like how quickly work gets done?
You're exactly right. Power is all about the rate at which work is done. A powerful engine can do work quickly, allowing a car to accelerate rapidly.
So if two people lift the same weight to the same height, but one does it faster, the faster person is exerting more power.
You got it. And we can express this mathematically. Average power is calculated by dividing the work done by the time it takes. Instantaneous power is force multiplied by velocity.
So even if the same amount of work is done, the power output can be different depending on how quickly it happens.
Exactly.
That makes sense. Like lifting that heavy box quickly feels way harder than doing it slowly, even if I'm technically doing the same amount of work.
Exactly. Power gives us a way to understand not just the work being done, but also the speed at which it's happening.
Okay, this is all starting to click. We've covered work, kinetic energy, power. And I have a feeling we're just scratching the surface here.
We are. There's so much more to explore, like the fascinating differences between conservative and non-conservative forces and the whole concept of potential energy.
I am ready for the next level of this deep dive. Every concept we unpack seems to unlock a whole new level of understanding.
I agree. Let's keep going. There are even more fascinating connections and practical applications waiting for us to discover.
Okay, so we've laid some groundwork with work, kinetic energy, and power. Now let's dive into this idea of conservative and non-conservative forces. It sounds a bit mysterious.
Yeah, a little bit, but we can make it pretty relatable, I think. Imagine you're on a roller coaster.
Okay.
As you climb that first big hill, you're gaining potential energy. It's like storing up all the thrill for the ride ahead, right?
So potential energy is like that anticipation before the drop.
Exactly. And then as you zoom down the other side, that potential energy is transformed into kinetic energy, the energy of motion. Now, conservative forces like gravity are like a free pass on this roller coaster. You get back all the energy you put in, so you climb a hill, you gain potential energy. Go down the hill, you trade it for kinetic energy, no energy's lost.
So conservative forces are all about the conservation of energy.
Precisely. But then you've got those non-conservative forces. They're like the toll booth on the ride. They take a little bit of your energy each time you pass.
Oh, okay.
Friction is a classic example. It acts against motion, converting some of that kinetic energy into heat, which dissipates into the surroundings.
So with conservative forces, it's like a perfect energy exchange.
Right.
Potential to kinetic and back again. But with non-conservative forces, there's always a little bit of energy lost.
You've got it. And this distinction is really crucial for understanding how different systems behave. Gravity, electrostatic forces, spring forces, these are all conservative forces. They only care about your starting and ending points, not the path you take to get there.
So it's like if you're driving, it's like choosing a scenic route versus a direct highway, right?
Right.
With conservative forces, you end up at the same destination with the same amount of energy, regardless of how you got there.
Exactly. But non-conservative forces, friction, air resistance,
Yeah.
they care about every inch of your journey.
Oh, wow.
They're going to siphon off energy along the way. That's why a car needs to keep burning fuel to maintain a constant speed. It's constantly battling that friction.
That's a great real-world connection. Now, we talked about potential energy in the context of that roller coaster. Can you maybe elaborate on that a little bit more?
Sure. So potential energy is all about stored energy.
Okay.
The energy an object possesses due to its position or its configuration within a force field. Think of a stretched rubber band. It's full of potential energy ready to be released.
So potential energy is like that coiled up tension waiting to be released.
Exactly. And the key point here is potential energy is always associated with a conservative force.
So the higher I lift a book, the more gravitational potential energy it has.
Right.
Because of its position. And the more I compress a spring, the more potential energy it stores.
You're getting it. And this brings us to a truly fundamental principle in physics, the conservation of mechanical energy.
Oh, okay. This sounds important. What's the big idea?
In a system where only conservative forces are at play, the total mechanical energy, that is, the sum of the kinetic and potential energy, stays constant.
Wow.
It's like a cosmic bank account, where energy can be withdrawn from one account, deposited into another, but the total balance always stays the same.
So even though the kinetic and potential energy of an object might be constantly changing as it moves, the total amount of energy never changes.
That's the beauty of it.
Wow.
It's a principle that applies across a huge range of phenomena. Think about a pendulum swinging back and forth. At its highest point, it's momentarily at rest. So all of its energy is potential energy. As it swings down, that potential energy is converted into kinetic energy, reaches maximum speed at the bottom, then as it swings back up, the process reverses. Kinetic energy back into potential.
So it's a constant dance between potential and kinetic energy, but the total energy stays the same.
It is.
Okay, good.
And this principle isn't just for pendulums. It applies to all sorts of systems, from planets orbiting stars to electrons whizzing around atoms.
It's really amazing how elegantly the universe is put together. Like from defining work to exploring this idea of energy conservation, it's all interconnected. But I got to admit, I'm a little intimidated by the idea of actually applying these concepts.
I understand. It's one thing to grasp the ideas in theory, but another to see how they play out in real-world scenarios. So why don't we do just that? Let's tackle a classic physics problem that brings together a lot of the concepts we've been discussing.
Okay, I'm game.
All right. Imagine a ball swinging on a string in a vertical loop. Think of it like a miniature upside-down roller coaster. The question is, how fast does that ball need to be moving at the bottom of the loop to make it all the way around without that string going slack?
That's a good one. I know it needs enough speed to overcome gravity at the top, but I'm not sure how to calculate that.
This is where our understanding of energy conservation and forces comes in.
Right.
At the bottom of the loop, the ball has maximum kinetic energy and minimum potential energy.
Okay.
As it climbs the loop, it loses kinetic energy and gains potential energy.
So it's like trading speed for height.
Exactly. Now, for the ball to just complete the loop, it needs enough kinetic energy at the top to keep that string taut.
Okay.
That is to counteract the force of gravity pulling it down. If it's moving too slowly, the string will go slack and the ball will fall.
So there's like a minimum speed threshold for it to make it around.
Precisely. And we can actually calculate that minimum speed using the principles we've been talking about.
Right.
It involves considering the radius of the loop, the acceleration due to gravity, and the conservation of mechanical energy.
Now I'm really seeing how these seemingly abstract concepts actually have very real-world implications.
They do, and this is just one example. These principles of work, power, and energy are constantly at work all around us, even if we don't always see them.
This deep dive is really opening my eyes to the hidden physics of everyday life. I'm excited to see where we go next. That vertical loop problem was really cool.
Yeah.
It's amazing how we can use work, power, and energy to analyze motion in such a dynamic system.
It's true, and that's just one example. I mean, these principles are at play everywhere.
Right.
The design of roller coasters, the launch of rockets, even in how our own bodies move and function.
Speaking of our bodies, it makes me think about exercise and sports.
Oh, yeah, absolutely. When you lift weights, you're doing work against gravity. You're increasing the potential energy of the weights. When you run, you're converting chemical energy stored in your body into kinetic energy. Even things like yoga or stretching involve forces, energy, and work, just on a smaller scale.
We really are walking, talking physics.
That's right. And understanding these principles, I think, it can help athletes improve performance.
Yeah.
Trainers can design better workouts. It can even help us make healthier choices.
Right.
For example, knowing that it takes more power to climb stairs quickly versus slowly
Yeah.
might motivate you to take those steps 2 at a time,
Yeah.
Get a little more intense workout.
I feel like we've been on this incredible journey through physics today, right?
We have.
We started with these simple definitions of work and energy, but then we uncovered these deep interconnected principles that govern motion in the universe.
Yeah, it's been quite a deep dive.
It really has.
And we've covered a lot. But, I think we've only just scratched the surface. There's so much more out there.
Oh, yeah, for sure. So to wrap things up, can we maybe do a super quick recap of the key takeaways?
Absolutely. We started by defining work as force applied over a distance.
Okay.
Only done when the force and the movement are in the same direction. We explored how work can be a positive, negative, or even zero, depending on the situation.
Right.
Then we jumped into kinetic energy, the energy of motion, and how it's affected by both the mass and velocity of an object.
Yeah.
And then we connected work and kinetic energy with that work energy theorem. Remember, the work done on an object equals the change in its kinetic energy.
Right.
We also talked about power, the rate at which work is done, and how it helps us understand the speed and efficiency of energy transfer. We learned about those conservative forces that conserve mechanical energy and those non-conservative forces that lead to some energy loss.
Yep.
We explored potential energy, the energy stored in a system due to its position. And we saw how it's always associated with conservative forces.
Right.
And how that can be converted into kinetic energy and back again, illustrating that principle of conservation of mechanical energy.
It's really cool.
It is.
We even tackled that physics problem, the ball swinging in the loop.
Oh, yeah.
Which shows how these abstract concepts have real-world implications.
Exactly.
This deep dive has been truly amazing. It's made me realize that physics isn't just about equations and formulas.
No.
It's a way of understanding these fundamental principles that govern how everything works, from tiny particles to, huge celestial bodies.
I couldn't agree more. And for everyone listening, I encourage you to keep exploring these ideas. Just look around you, observe the world in motion. Ask yourself, how are work, power, and energy at play here?
Yeah.
You'll be amazed at what you discover.
Thank you so much for joining us for this deep dive into work, power, and energy. We'll see you next time.